All right, full disclosure, everyone. I am sitting outside at my house with my dog, and there are dogs barking, so this could go horribly wrong. But hoping that we can get through a little bit of a video today. So you heard from Mr. Smedes about the Coriolis effect. Now we're going to talk about solar radiation and the Earth's seasons. So we're going to talk a little bit about how the Earth is impacted by the sun in terms of seasons and weather. So remember that insolation, or if you don't know, insolation is the amount of solar radiation or energy from the sun's rays that's reaching an area. And insolation is measured in watts per meter squared. So how much energy is reaching the Earth's surface from the sun in watts per meter squared. Your essential knowledge and your learning objective is explain how the sun's energy affects the Earth's surface, and the essential knowledge is listed here for you. We're going to hit all of these today. As we go forward, you're going to notice I don't stop on these slides every time. Feel free to pause and take a look at those things, but you'll hit all of these essential knowledge pieces in this session. So, solar intensity is is how much light energy is coming from the sun, and the angle of the Earth, or how the rays strike the Earth's surface, and the amount of atmosphere that the sun's rays has to pass through is what impacts the intensity of the sun's rays. At the equator, you have higher insolation than you do at the higher latitudes. At the higher latitudes, the sun has to pass through more atmosphere, and it's at a higher angle, so it loses more of its energy than at the equator. At those angles, you're almost getting direct sunlight, so it's not passing through as much atmosphere, which means higher insolation, higher solar intensity. It's also spread over sort of a larger surface of area than at the equator. So take a look. This is showing you direct. You're getting 400 watts per meter at the equator, and at the poles or further north, you're getting 200 watts per meter. Which is one of the reasons why solar panels are more effective in places like Arizona, in the southern part of the United States, because it is further south to the equator. Not obviously the equator, but you're still getting higher watts per meter than up here. The solar intensity also impacts the seasons. So you know that the Earth orbits around the sun, and it also is tilted on an axis, so it spins, and as it's spinning on its axis as well. That orbit and tilt changes the angle of the sun's rays, which causes varying insolation, varying length of day, and a variety of seasons. The tilt of the Earth's axis stays fixed during orbit, so the tilt is always the same as it goes around the sun. In June and December, those solstices in the northern or southern hemisphere are either maximally tilted toward the sun or away from the sun, which creates summer and winter. So obviously in June, it's maximally tilted towards the sun, and in December, it's tilted away from the sun. In March and September, in the northern and southern hemispheres, they're equally facing the sun. So you're having a different variety of solar intensity happening at those places. That tilt of the Earth's axis causes variation in the angle of insolation, which changes the intensity, which we just talked about, the length of day, and the season. So if you look here, this March equinox, the equator is receiving the most direct insolation. You're getting 12 hours of sunlight in the northern and southern hemispheres, and that's where you see spring and fall, so you're going to have more mild temperatures in the southern hemisphere. The northern hemisphere will be spring and the southern hemisphere would be fall, but they're still mild temperatures. In June, you see the northern hemisphere is maximally tilted toward the sun, which is the longest day, which is the start of summer. And the shortest day in the southern hemisphere, which is the winter. So you'll notice the top of the northern hemisphere here is tilted towards the sun, and the southern hemisphere is tilted away from the sun. So 3 is the September equinox. It's not listed here, but the September equinox. Go back. That's when the equator receives the most direct insolation. Again, the northern and southern hemisphere are getting 12 hours of sunlight. It's the fall in the northern hemisphere and the spring in the southern hemisphere. And then finally, the December solstice, the southern hemisphere is tilted toward the sun, which is the longest day or the start of summer in the southern hemisphere, and the shortest day or the start of winter in the northern hemisphere. I'm struggling with the words today. With all of this, we also have to discuss albedo. Albedo is the proportion of light that's reflected by a surface. Surfaces that have a higher albedo are going to reflect more light and absorb less, which means that it's going to be cooler, so it's going to absorb less heat. So that means things like snow and ice, they actually help keep the earth cool because they're reflecting light away from the earth. Whereas darker surfaces, water that doesn't have snow and ice, paved land, any sort of land that is developed is going to absorb more heat because it has a lower albedo, so it reflects less light, which means it actually warms the Earth's surface rather than cooling it. So surface albedo then obviously albedo obviously directs surface temperature, because if the sunlight is absorbed by the surface, it gives off infrared heat, which makes it warmer. So areas that have a lower albedo are going to absorb more sunlight, which means it's going to be warmer. So this creates what we call an urban heat island. Urban heat islands are areas that are hotter than the surrounding rural area because of paved surfaces, blacktop, buildings, where you see forested areas taken away. That's going to create what we call a urban heat island, which means it's hotter there than it is maybe in the suburbs. The polar regions are cooler, mostly due to the higher albedo of the sea ice and any land ice that's there. That's going to reflect off a lot of heat. I had to restart because my dog started barking. Okay, so practice FRQ. Identify which season is taking place in the northern hemisphere in this diagram. Describe how the tilt of the Earth's axis is responsible for the Earth seasons. Remember, it's the tilt of the axis, not the shape of the orbit. That is a misconception that a lot of people still have. The Earth's orbit is not oblong enough to create differences in the Earth's seasons. It's the tilt of the axis that makes that happen. All right, guys, have a good night. You're welcome. Happy Earth System Zing. Have a good night.